Hello, it's John back again. I was talking to another teacher recently who was talking about singing to start their videos, going for a Dora the Explorer feel. But I, like you guys, I'm going to spare you that. Although if a chance comes up to sing I'm the map, I'm the map, I might go for it. All right, so this is just a quick video to talk through how I think about one of these function families where we're getting more than one function defined by a parameter. So in this case, it's activity 322 from Active Calculus by Matt Bulgans. And as a changes, the function's going to change, right? So when I'm looking at this, even before I read on, I'm already thinking a little bit about cubic functions. What do I know about cubic functions? I know they can have kind of this wavy sort of design. As I look at that x cubed minus ax, I'm thinking that, well, I could factor an x out. So it's like a parabola times a line. I notice that this is going to be different depending on a. If a is positive, like x squared minus 4, that has two solutions, x equals 2 and x equals negative 2, meaning it'll be two places where it's 0. So this function will have a root at 0. And if a is positive, it'll have two roots, plus and minus the square root of a. If a is negative, I'm guessing that means no extra roots, right? Because there's no number we could put in for x that would make x squared plus 4 0. So we're not going to get any extra roots. So it's only got the one root at 0. So I'm guessing that that means it kind of straightens out. Now it's okay if you don't have all these things you think about, right? This is from a lot of years of experience thinking about functions. But what I'm trying to do is to just kind of open up my head and think aloud as to what I notice when this is happening. Okay, so before I go farther into the activity, I'm just going to quick kind of read over the whole thing to see what's going on. Find p prime of x, find the derivative, and determine the critical numbers of p. So maybe I want to think about what does that mean to be a critical number of p. Mostly we think about that's where the derivative is 0 or undefined. So in this case, the derivative of a cubic is going to be a quadratic, so I'm guessing two critical numbers. We'll find them as we move on. Construct a first derivative sign chart for p. What can you say about the overall behavior of p if the constant a is positive? Okay, so they want us to be breaking down things into cases, much like what I did already, right? Thinking about it makes a difference if a is positive or negative. The shape of these two functions, I was guessing from experience, definitely critical numbers would be different. So I'm guessing that that's where that's going. All right, so find p double prime, the second derivative, and construct a second derivative sign chart. That tells us concavity. Where is it concave up, concave down? I think both of these look like it's going to have kind of one concave up part and one concave down part. In this one, even though it's more subtle, right? It doesn't have that kind of cup shape. So I'm guessing that that'll be the case for that. Now you notice I'm kind of making predictions before I've even started. One of the things we know in math education is that if you make predictions, for one, it helps you construct what's called a schema. So kind of a framework of knowledge, gives you a place to kind of organize what you do, what you find out. It also engages you a little more, like as you do the work, you find out whether your prediction was correct or incorrect, how it could be sharpened, right? So you're kind of paying attention a little bit more as you go through. And at the end, it also gives you some the start of thinking about how to check your work, right? So if it's really different than my prediction, maybe something went wrong along the way, and it gives me an incentive to check. All right. Without using a graphing utility, see, it's good I'm reading through, because otherwise the very first thing I would have done would be to graph this somewhere, and I might still do that, right? So, without using a graphing utility, sketch and label typical graphs of p of x for the cases where a is greater than 0 and a is less than 0. Label all inflection points and local extrema. So I kind of did a first guess at that already, but we want to use the kind of the calculus information we've got to think about that a little more. And then it says, finally, use a graphing utility to test your observations above by entering and plotting the function p of x equals x cubed minus ax for at least 4 different values of a. I'll write several sentences to describe your overall conclusions about how the behavior of p depends on a. So in other words, we've got this family of functions. We have a parameter that we want to imagine being able to change the values. We want to be able to describe the effect that that parameter has on that family of functions. Okay. So let's dig in a little more. Let's just think about these first two ones. So find p prime of x. So the derivative of x cubed, 3x squared. It's not an exponential, it's a polynomial term. And then the derivative of minus a times x. So a, even though it looks like a variable, we're thinking about it as an unspecified number. Again, to talk about the math a little bit, one of the difficulties learners have transitioning into algebra and then into calculus is thinking about variables the way mathematicians do, which is much more about relationship. Right? Often when you're introduced to variables, it's representing some unknown. But by the time we get to stuff like p of x equals x cubed minus ax, we're thinking about the variable as a relationship, right? An input, and then we're getting this output, x cubed minus ax, and we're thinking about how are those connected, right? So x isn't representing some number we don't know. It's this variable idea is a little more distinct than that. Okay, so I could just as well think about this as minus 2x. And the derivative of minus 2x is going to be the constant minus 2. So same thing in this case, the derivative is the constant minus a. So, so it's a constant, even though we've got this fancy name for it, parameter. Okay, so when is this equal to 0? When x squared is equal to a over 3, so x equals plus or minus square root of a over 3. I could have put a couple extra algebra steps in there, but I'm not worried about it. If you're confident in your algebra and you can skip steps, that's not a make or break. It's not talking about calculus understanding. On the other hand, if skipping steps makes you make mistakes, then be careful and take every step. Okay, so this is saying that on either side of the 0, determined by the square root of a thirds, there is a critical point. Okay, so this already means kind of thinking about that in this cases way. So if a is equal to 0, the only critical point is x is equal to 0. If a is greater than 0, that works. We get 2 critical points. If a is less than 0, we get imaginary values out, which means no critical points. And we're not going to dig into this too much, but turns out there's still a meaning to that, right? That those are special values for the function. That if we did more math with complex numbers, we'd be finding that out. Okay, so if we think about first derivative sine chart, they're talking about this case where a is positive and we have two places, right? So regardless of whether a is positive, we get a parabola opening up. So we've got these two roots. And then it's a pretty steep parabola. At 0, it's going to have this value minus a. It opens up pretty quickly, so it's positive before that first root. It's negative before that second root. And it's positive afterwards. Okay, so in other words, this is for the derivative, p prime. So that means the function's increasing, decreasing, increasing, which in a cubic means we're talking about something with that kind of pattern. If a is less than 0, that would be like -2. So that would wind up being 3x squared plus 2. So that's something that's always positive, right? This is still minus a. So in our case of thinking about a as -2, that would be up to 2 because we have 3x squared minus a -2. And then it's going to open up from there. So no roots. Always positive. All right. So, and if a is 0, we just have 3x squared. That's always positive, and it would be just touching the axis there. So that's a critical point, even though it's going to turn out in the function not to be a local min or a local max, right? So that happens sometimes, and we have that x squared multiplied in there, so that kind of makes sort of a redundancy. Interesting thinking about the effect of that on the graph. All right, so let me look over. Each case describes the relative extremes of p. I didn't think about that at all. So in this case, it's going to have a local maximum when it switches from increasing to decreasing, and a local minimum. And there's no global minimum because it goes off, keeps decreasing going out that way, and it keeps increasing going out this way, so no global maximum. And then this one is just always increasing, right? So there's not going to be local or global extrema. Okay, so let me look one more. All right, part C, think about the second derivative. So remembering the first derivative was 3x squared minus a. So the second derivative is going to be 6x, and then the derivative of a constant is 0. So I could put a plus 0 there, but I'm remembering that I'm taking the derivative with respect to x. So the a doesn't have any x's in it. It's just a separate number. Doesn't change when x changes, so its derivative is 0. So if we think about when is the second derivative equal to 0, well, that's pretty clearly going to be when x is equal to 0. Okay, So, and then the second derivative is going to be negative if x is negative. So that's concave down. And it's going to be positive if x is positive, which means concave up. It writes the exact same thing again, which means concave up. Okay. So that's kind of my second derivative sign chart. What does it tell me about the concavity? I already thought about that. What role does A play in determining the concavity of P? It doesn't play any role. There's no A in the second derivative. So regardless of what A is, it doesn't make an effect. Now, would that be different if it was minus ax squared? Definitely, because then with the first derivative would have had a minus 2ax, and then the first derivative, and then the second derivative would have a minus 2a in it, so it would definitely change the effect. Right? So kind of having a quadratic term is very different than having a linear term with the cubic. That might be worth investigating on your own. Okay, so without using a graphing utility, sketch and label typical graphs of p of x for the cases where a is greater than 0 and a is less than 0. I feel like I've kind of already done this. All right, so I know the point is going when x is 0, and this is the original function, I get 0 out. So it's always going to cross through here. And I know it's concave down on the left side and concave up on the right side. It has a root figured out back on that first slide if a is greater than 0. And it's concave down, increasing, decreasing, decreasing, increasing. Oops. So it changes concavity at 0. My roots are plus or minus square root of a third. And then I want to be able to label these critical points. And if I look back, oh, those were the critical points I labeled. What were the roots? Plus or minus square root of a. Pays to have all your work on one page. All right, so the roots were at plus or minus square root of a. And that makes sense then, plus or minus square root of a thirds, all under the square root, are going to be the critical points. Okay. Finally, use a graphing utility, test your observations above by entering and plotting the function p of x equals x cubed minus ax. So we could definitely use Desmos. I'm going to use GeoGebra just because you probably have used that a little less, and we'll see what happens, right? I mostly use the desktop GeoGebra instead of this online, but it's pretty intuitive. If I sign in, then I'd be able to save my file. It might sign me in automatically because if you're looking at my tabs up above, you can see I have bunches of GeoGebra open as it is. Okay, so I've got my p of x. Now what's going to happen if I just type it in with my arrow to get out of the superscript? It was minus ax. Oh, it gave me a slider. Okay, so as it gets more positive, those bumps get more pronounced. Once I get negative, they get less and less and less pronounced. It almost even looks like it's getting linear, but really it's just increasing and decreasing so quickly it's hard to see. Okay, so does GeoGebra know how to do the derivative when it has a parameter in it? Let's see. Pre prime of x. Oh, it tells me the particular value depending on what a is. So as a changes, we can see it having the value here. So I know this is 3x squared minus a. And the second derivative, I'm expecting a line that passes through the origin, and that's what I get. Okay, so I think that confirms everything that we said about it. It checks whether I was taking the derivatives correctly, checks our sense of what was important. Now, GeoGebra also does kind of these important points, right? So the extremum is, this says is that x is equal to 0.9. So I said that that was going to be the square root of a divided by 3, which is 0.9. So I can even check that kind of information. And the root is at 1.50. Again, some rounding going on there. And we said that the root was going to be at the square root of a, and we get 1.5. Okay, so we're completely verified. We're justified. We finished an activity. So I'm asking you to think about one of those next two activities on your own or with a partner. So thanks very much for watching. If you have questions, you can always ask them directly or put them in the comments. I'm happy to answer them. Thanks very much, and have fun with families of functions.